In this video, we're going to learn about resting membrane potential. This is a neuron. The resting membrane potential is the electrical potential, or voltage, across the membrane when the neuron is at rest, meaning that an action potential is not occurring. Resting membrane potential is equal to about -65 millivolts. The membrane potential arises because there's a slight excess of positive charges on one side of the membrane and negative charges on the other. This imbalance exists right at the membrane interface, so areas farther away from the membrane are electrically neutral. Also, the difference in the number of positive and negative ions on each side of the membrane involves a very small number of ions compared to the total number of ions, so moving only a small number of ions can change the membrane potential. There are two main forces that influence membrane potential: the chemical or diffusion gradient and the electrical gradient. The chemical gradient refers to the fact that ions move down their concentration gradient from areas of high concentration to areas of low concentration. The electrical gradient refers to the fact that ions with like charges repel and ions with opposite charges attract. When too many like charges accumulate on one side, it pushes some of the charges back across the membrane. Equilibrium potential for any one ion is established when the diffusion force equals the electrical force. At this point, there is no net movement of that ion. No net movement means that ions are moving across the membrane in both directions, but at the same rate. Equilibrium potential is different for different ions. These values are determined by the Nernst equation, which calculates equilibrium potential based on the concentration of the ion inside and outside of the cell, as well as the valence of the ion. When the concentration of an ion is higher outside the cell than inside, the concentration ratio is greater than 1, so the logarithm output is positive. For positively charged ions, this makes equilibrium potential positive. Conversely, when the concentration is higher inside than outside, the ratio is less than 1, making the logarithm output negative and equilibrium potential negative. For negatively charged ions, this relationship is reversed because the sign of Z is negative. The ions that contribute the most to the membrane potential are sodium and potassium. When we plug in the values for concentration and valence into the Nernst equation, we get that the equilibrium potential for sodium is equal to +62 millivolts, and the equilibrium potential for potassium is equal to -80 millivolts. There are other ions that contribute to the membrane potential of a neuron. These include the calcium ion, which has an equilibrium potential of +123 millivolts, and the chloride ion, which has an equilibrium potential of -65 millivolts. These are approximate values and can vary. Now that we understand the equilibrium potential for different ions, let's take a closer look at the neuronal membrane to understand why the resting membrane potential is -65 millivolts, and how sodium and potassium ion concentrations are maintained. First, we have leakage potassium channels. There are many potassium channels in the membrane that are constantly leaking out potassium. These leakage potassium channels are largely responsible for the resting membrane potential because the membrane is about 40 times more permeable to potassium than sodium. This explains why the resting membrane potential, which is about -65 millivolts, is much closer to the equilibrium potential for potassium than for sodium. If the membrane were only permeable to potassium, then the resting membrane potential would equal -80 millivolts, and if the membrane were only permeable to sodium, then the resting membrane potential would equal +62 millivolts. Also in the membrane we have the sodium-potassium pump. The sodium-potassium pump is responsible for maintaining sodium and potassium concentrations. The sodium-potassium pump moves 3 sodium ions out of the cell and brings 2 potassium ions into the cell. It runs constantly and moves sodium and potassium against their concentration gradients, which takes energy in the form of ATP. As a result, potassium is 20 times more concentrated inside the cell and sodium is 10 times more concentrated outside the cell. To remember this, you can use the salty banana mnemonic. In summary, resting membrane potential is determined by the equilibrium potentials of different ions, weighted by the relative permeability of the membrane to each ion. Thank you so much for watching, and I hope you found this video helpful.